Hi, students. It's Miss Parrot, and these notes are about coral reefs. Yay!
Coral reefs are biodiverse, provide food, shelter, and medicine. And that's her daughter.
Hi, students. It's me, Miss Parrot. Let me try to make this full screen. But why? Okay, it's coral reefs. So I went a little bit out of order. The part that you're going to look for right now is the page, I think it's the second page, what the phylum corals are in and what that means. I changed the order a little bit, but I'll prompt you with these. Okay, the classification they belong to. So corals are a part of the phylum Cnidaria, and very soon we're going to talk about the different classifications. So from regular biology, you guys should have covered that organisms are classified by domain, kingdom, phylum, class, order, family, genus, and then species. And it's all based on very broad characteristics that they share, getting down to very, very specific and detailed characteristics. I had a little sticky note that said, don't say so hopefully I can do without it. I almost did. Okay. Phylum. All right. We are in phylum Chordata, for example. So that it means a whole bunch of things, but like we have a spinal cord. They are in phylum Cnidaria. The C is silent. So that means all organisms that are in that phylum are aquatic organisms or aquatic ecosystems, primarily marine. They all have cells called cnidocytes. Those are stinging cells, and they're used to capture prey. This is why we can get a sting from a jellyfish or from an anemone or some corals, or even like the Portuguese man of war. With that being said, real quick about the phylum, if they're in phylum Cnidaria, that means they have to be in the kingdom Animalia, because they're not a plant, they're not a fungus, they're not a protist, like a one cell, single cell animal. And being in kingdom Animalia means that they are going to be carnivores. They're not producers. So they're going to primarily eat meat. They can move, whether it might not be they move their whole organism, but they do have a response to stimuli. They grow. They're multicellular. I think those are all the kingdoms for the Animalia. And then the domain, which is the most broad category, they're in domain Eukarya. And again, from regular bio, if you are in eukarya, that means you're a eukaryote, which means your cells have a nucleus. If you are not in the domain eukarya, then you are in the domain prokarya. Pro meaning before, karya literally comes from kernel, which means like the kernel of the cell, the nucleus of the cell. So prokarya, before the nucleus of the cell, those would be like bacterial species. Anyway, we'll cover that very shortly. But they're from phylum Cnidaria. I put a star bullet with it because this has been asked actually on the A-level test again, and it has also been asked in the AS level test, I believe, last year. So you don't need to know the different organisms that are also in that same phylum. I just put it there just to give some more association. There have been times that it's mentioned that an anemone is in that same phylum, but Cnidarians have cnidocytes, which are stinging cells, like a harpoon-like cell. Now we're going to be in the page that looks like this. It's the front of the second page, or page 3. Okay. To be a coral, this is just their basic anatomy on this side. So they spend most of their adult life as polyps, just one individual polyp. Same with anemones. They form colonies when they grow together. And one organism is really small. So to actually make a coral reef, there could be billions of these. It's a lot. They're sessile, which means they're non-moving. Sessile is actually an A-level term, so that's why I put what it means there. But they don't move, like they're sedentary. They cement themselves. They don't move. When they are in their larval phase, they're zooplankton. So zoo meaning animal, plankton floater, and they freely float in the water column carried by currents. When they get to a hard substrate, then they will cement themselves to that substrate. A lot of them don't make it. It's okay though. Their adult life, they are called polyps, one coral polyp, and they form colonies. They attach themselves to a rocky substrate, and their body is really quite simple. So they have just a cylinder of epidermal tissue. And I'm going to predict that you're probably doing this after the open ocean notes. So then you should be familiar with epi. Epi meaning top of. And you also have an epidermis. So I'm certain that this isn't something brand new. Epidermal would mean like the top of, like the top layer. So they have a cylinder of epidermal tissue. And the cylinder that they're talking about, I need to remember to erase this, is like right here. Here we go. That's a cylinder. They have tentacles that will surround their mouth for feeding. This is their mouth, just in this area. And then the tentacles come out from the sides. And their mouth is going to just lead to a simple stomach that has digestive enzymes that are secreted to digest organisms. Similar to ours, but much more primitive. So once you enter in through the mouth, then you're literally in the stomach. And the food that they eat is going to be mainly phytoplankton and smaller zooplankton. They're very simple organisms. They're not hard to digest. It would not take a ton of enzymes to break that down. Cool. How they feed. So the polyps, again, that's the individual. They have tentacles that will capture prey. It also deters predators. It's the reason why we avoid jellyfish, literally. The tentacles themselves are lined with those cnidocytes that make them cnidarians. Cytes, like cyto means cell. And you have like a microscopic version of them shooting out. And it's painful because a lot of them will contain like a toxin in there, and it is to deter predators or also to help them feed. The cnidocytes have a nematocyst. It's like the needle portion. You can see it better on this picture here that I'm kind of circling. This second picture, you can see that like that needle come out, and that is the nematocyst. Cyst is also like cellular. And those come out of the cnidocytes. That's why it hurts. It's microscopic, and there's a lot of them at once. There's a strand, similar to a harpoon. If we harpoon something, we are going to have like a rope attached to it so we can pull it back. But the strand connected to the nematocyst and the cnidocyte will bring the prey to the polyp's mouth, and then it can go back into their stomach. Okay, so the cell that they have is called a cnidocyte. That's what make these organisms in the phylum Cnidaria. Inside of the cnidocyte is a needle-like harpoon called a nematocyst. How they're going to attach themselves to the substrate. So they attach themselves to the rocky substrate. They need a hard substrate. These are not burrowers. So no sand. A rocky substrate using a basal plate. Basal means bottom. I'm just thinking about basal cell carcinoma and I'm making word association. I'm sure you can see my brain thinking. Basal means bottom. So that's how they attach themselves. BB, basal bottom. So this is a basal plate. Its definition is it's the part of the coral that separates itself from the substrate. And that's because it literally does. It's what is in between the coral organism and the substrate. It attaches itself to the substrate. Basal plate on here. This would be a great time to use the colors. Basal plate would be like this right here. You have a different picture, which is also on these slides. They protect themselves with a cup-like structure called a calyx. I emphasized and increased the font of the C's, the cup calyx. And this is like what they're sitting in a cup. They're placed in a little cup. That would be the cup. And there's thin walls on the cup calyx called theca. So theca, thin. This is like the epidermal walls. They're like very simple. It's just one layer and then you're like into the organism. Right here. I kind of went out of line, but those. This would be the theca. Theca, thin walls. I don't know why I duplicated that. Corals attach themselves to rocky substrate using a basal plate. I can't. I can't deal. Thanks for your patience. Okay, and then they connect their calyxes, so their cups can be connected because that's how they form their colony to create a skeleton made of calcium carbonate for protection. And they secrete this. They create the calcium carbonate, so they're connected this way. Same way like that we can make keratin, biotin. They just make calcium carbonate. Okay, so you have this blank version. And there you go. So take a moment and make sure you label it. Last year, we lost some points for not labeling. One of the challenge questions that I've seen it once, but the syllabus is relatively new, was to describe and explain. I can't show it on this tab though. This is only recording this tab. I'll tell you right now. I don't think you can see what this tab is on the exam questions. Describe the main structural features of a typical coral polyp and state the function of each feature. You may use label diagrams, which I would always encourage. That question is 10 marks. I feel like every time we advance a section, we see the marks increase, and that is not on purpose. So that's one of the things when we do like a review sessions that we'll practice, because we get thrown in one of these, or even if it's still like 6 marks, like it's still worthy of being able to describe these features. And that's something just through practice and repetition that, I imagine you don't draw this often, probably never at all. So through practice and repetition, you can kind of get this structure down and then label and say what it's for. Please label. Okay, we're going to move on to this next section. I think it's on the second page. But it's compare the 2 types of corals with examples. Okay. I don't have any transitions, and I'm fine with it, or any like animations. Okay, so there's 2 types of corals. There's only 2. There's essentially hard corals and soft corals. So ones that I collect in my room, the carcasses, really that's the only ones that we can take, because soft corals will smell really bad because they're soft. Like they don't have just like a skeleton, and they're frail. They'll fall apart. Where can I go that I'm not in the way? I guess I'll go in the corner. All right. There's names for them. So the hard coral is called hermatypic. Hermatypic. Hard hermatypic. The H can be an association, or when I think of it, I think like herma, like a hermit. If something's like a hermit, it's going to like stay in its place. It's not going to move. These are hard corals. But these are your reef building corals, and they can build off of each other. They live in colonies, and they will always contain zooxanthellae. We're going to see that word a lot coming up. Zooxanthellae. You can say zooxanthellae. It doesn't matter. It's potato. It doesn't matter. They always contain zooxanthellae. Okay. Zooxanthellae is a symbiotic photosynthetic. I haven't gone to sleep yet. If you were in class today, you know that I was awake since 4. No, I didn't go to bed till 4. Anyways, hence why you have the open ocean notes. Zooxanthellae is a symbiotic, which means it has a relationship with, it's going to have a relationship with the corals. Photosynthetic, so it does photosynthesis. Dinoflagellate. A dinoflagellate is a type of algae. It's a type of phytoplankton, actually. And when, just to, again, put like association with things that this hopefully isn't the first time you're hearing dinoflagellate. In the Indian River Lagoon, when there's bioluminescence, and people do like bioluminescent paddleboarding and all that jazz, in October and September and August, when the river's warm enough for this, it's dinoflagellates that are doing the, I said it twice, bioluminescence. So they're symbiotic, have a relationship with, photosynthetic, does photosynthesis, dinoflagellate, which means it's an algae species, but does photosynthesis, living inside the tissues of many invertebrates, things that don't have a backbone. Literally for this situation, we're only going to talk about them being in corals. Other places they can live would be like a giant clam. Giant clams are giant, and they are in coral reef ecosystems. But that is not what we're here to discuss today. We need to associate them with the hard corals, the ones that build. If a coral dies, another one will grow in its place and add another layer of calcium carbonate. This is how we can get these varying structures that we see. And these are the hard corals. They don't really bend. Ahermatypic. So if hermatypic means that you are a hard coral, then ahermatypic, just like abiotic means not alive, ahermatypic means not hard coral. So these are softer corals. like a sea fan or a sea whip. You have a big fan right here, the red one. So they do not build on each other. Like its organism can grow, but it's not like it's building these colonies one by one by one by one by one. And they do not contain zooxanthellae. They're getting nutrition just by like filter feeding, just dusting the ocean. They're flexible. They do not create coral skeletons. They look more like a plant or like a tree that's branching. They do not have a symbiotic relationship with zooxanthellae. So they do not have any sort of relationship with zooxanthellae. Okay, the next part you're going to be on, I believe this is on the back of the front page. Describe the symbiotic relationship corals have with zooxanthellae. We're looking for its type of relationship. What does a zooxanthellae perform? I actually already mentioned it. State its trophic level, which is not directly on the slide, but it should be able to be inferred. Specifically, how does zooxanthellae benefit the coral, and how does the coral benefit zooxanthellae? I'm emphasizing to be specific about it because these are exam questions, common exam questions about describe how. Things we're not going to say is one does blah, 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 and the other, because their names are not one and the other, zooxanthellae or coral. If you're going to be writing zooxanthellae a lot, you very well may. After you've written it maybe 2 or 3 times, then I start to just abbreviate it with zooxan, Zooxan, and that's good. If that's not enough for you, then just write it all out. If you're wondering, do you have to spell that right? Kind of. If you don't get the double L and you don't get the AE, like the Latin AE at the end, that's okay. It can't be confused with zooplankton. It's not the same thing, but they can infer. So that's what we're looking for on your paper. Please be specific. All right, they have a mutualistic relationship. Again, something you've probably learned about in previous science classes, but definitely should have learned in biology. Without having this relationship, hard corals would not be able to create large reefs. So they do have a mutualistic relationship with zooxanthellae. And I'm going to kind of emphasize the difference between what's mutualism and then what is symbiosis. Symbiosis means you have a relationship, period. That's it. It doesn't describe what the relationship is like. So we can't say they have symbiosis. Like if you have a relationship with something positive, negative, or neutral, it's symbiosis. But specifically, this is a mutualistic symbiotic relationship because they're both going to benefit each other. They're both benefiting. That is also important whenever you're talking about symbiotic relationships. Both benefit. They both benefit. Like, oh, you guys broke up? Who broke up with who? It was mutual. That means you both made that decision. Mutual. Same. Both. All right. The next slide is going to describe them, but just so you can imagine what this looks like, I have a cartoonish version. So inside their tentacles, but in their epidermal tissue, because they really don't have much other than that, you do have your photosynthetic zooxanthellae living in there. They do photosynthesis, sunlight. And it makes sense that they're on the tentacles and that the tissue is thin so that you can have the most amount of sunlight penetration. It'll be on further slides, but this is why corals actually have color. They do not produce color on their own. So some microscopic imaging, you can see zooxanthellae on the tissues at the bottom. Each of these darker purple is zooxanthellae. You can do that with certain staining. Same here with a light microscope. All these orange clusters are zooxanthellae living in the coral tissues. And what you actually see emerging here, like with the tentacles out, that is the coral polyp coming out of its calyx home, its little cup. Okay. I know this is wordy, but I didn't want to like shortchange you or anything. It is what it is. It is what it is. Where do I put my face? I can't make it smaller. Okay. So describe how hermatific corals, hard corals, and zooxanthellae have a mutualistic relationship. Notice the stars. So over here, zooxanthellae, it performs photosynthesis or does photosynthesis and produces organic material. If you don't want to say produce, you can say synthesize. That's lovely. If you don't want to say organic material, you can say glucose. You could also say carbohydrates, but you should know that glucose is a carbohydrate from photosynthesis. If not, jot it down. And the coral is able to use that for energy. So a way that I think of this, and it's nothing we're going to write and expect to get any marks on it, but it's like having a live-in chef. So a chef that lives with you. The chef is going to synthesize the food, make the food, produce the food. The chef is going to eat first. Like the zooxanthellae is going to be able to utilize its own organic material first. And then the coral is going to get an abundance of that as well. This means that corals do not have to feed all the time with their cnidocytes. Most of their nutrients are going to be given to them from the zooxanthellae doing photosynthesis. Additionally, corals are coral reefs should be very clear. They shouldn't be full of like detritus or like marine snow, little scraps sinking down. That would make the water really cloudy and it would not be good for photosynthesis. And the zooxanthellae this is where I would say that I've said this before in class, like this is the most like entitled ecosystem. It is the most like bougie ecosystem. They have the most demands. It's all because of the zooxanthellae. The zooxanthellae in here is your main producer. It's not seagrasses because seagrasses can't grow on a hard substrate. You can have some algae. There can be some algae, but it's not the dominant producer. Like phytoplanktons, it's not the dominant producer. This is it. This is the main producer. And if they don't like even the tiniest change in any of the conditions, which we'll talk about briefly and like shortly, they will leave. They will literally just exit themselves. And I have what that looks like on here. So yeah, the water is very clear. There really is not an abundance of detritus or debris settling down, like sinking down for the corals to be able to like sound effects, filter feed through the water. So having a reliable source of nutrients and organic material coming straight from the zooxanthellae inside of them is perfect. When I made that noise, it like really made me like my tongue itch. It's weird. On the other side, so then what do corals do? And we need to be specific. Corals can provide the zooxanthellae with there's only 3 perfect brackets remaining. That's distracting. I'm not one of them. Corals provide the zooxanthellae with the habitat inside of their tissues. I think that's the easiest one to remember. It takes like less descriptive statements. They also provide them with a steady source of carbon. Corals corals do respiration. So are we. So does everything that's alive, has to do cellular respiration in their mitochondria to synthesize ATP. They're constantly doing cellular respiration. And they release CO2 when they do that. Just like you are, I am. That's the waste product from doing that, from doing respiration. Zooxanthellae needs a constant, reliable supply of CO2 because zooxanthellae is a photosynthesizer. And in photosynthesis, your producers are taking in carbon dioxide and they are going to synthesize glucose and water and sunlight. But they don't have to go looking hard for water. It's right around. Glucose is a carbohydrate. They have carbon, oxygen. So there's your carbo and hydrogen in a carbohydrate. Hydrate. Carbon, oxygen, hydrogen, carbohydrate. Okay, sorry. Olive just asked for more screen time. Bless her heart. For these reasons, they both benefit. This is mutualistic. And we would say that. They both benefit. Okay, just another picture of them inside of the tissues. And again, this is the animal. These tentacles coming out are a part of the animal. And the zooxanthellae lives inside of the tissues. The tissues are very thin. And also, this is also the way that they breathe. That's an A-level topic, but just literally from oxygen diffusing through their thin tissue, and CO2 diffuses out, or it goes to the zooxanthellae. Ooh, it's picture time. Dang. Okay. I'm sorry. I'm so freaking sorry. Okay. Some people hate that. That's all of the individual coral polyps coming out. Inside their thin tissues and inside their tentacles would be the zooxanthellae. They also do this so they can filter feed. Literally just take in the organic material, if there is some, like that's in the water column. This is a hermitopic coral. Even though like the coral themselves have soft tissues, that's fine. I mean, you don't have anything. Can't even think that's like literally a skeleton. Its protective surface is made of calcium carbonate, the calyx that it sits in. Here you see a lot of hermitopic corals. There's a hermitopic mixed in there, but majority of them are actual reef builders that colonize and have zooxanthellae inside of them. Another one. I don't know if you heard that. It's silly. So these are also hermitopic corals. Even though they have a soft part that comes out, what they build reefs with is not this. What they build reefs with is the calcium carbonate skeleton that they secrete. They release that, create it, and release it. Isn't that fun? But that color, it has no business having that color. It wouldn't be helpful for the organism. The reason why it has that color is because of pigments inside the chloroplast. This is cool. I believe this is like something called like a mushroom coral. This is hermitopic. It is hard. Builds on itself. But what you're seeing here is a time lapse, and they will release like a mucus on top of their coral skeleton, and they'll leave it. And then anything that settles on it, any debris or detritus ends up settling on it. It's like a loogie. You suck back in. It's gross. But what a good adaptation. They're just collecting it throughout the day. These also are all hermaptipic corals. They're just very close up. They're out of their calcium carbonate skeleton. And you can see their mouth so clearly. They're very simple. They all have different colors. Because the zooxanthellae. Cute! Same. A hermaptipic coral. Not a hermaptipic. This is a hermaptipic coral. They build reefs. They're literally just coming out of their calyx. Okay. Front page. The front page, beginning. So we know the difference. Now we know kind of their simple body plan. And we know that hard corals are going to do or have photosynthesis because they have a mutualistic relationship with the zooxanthellae. The coral themselves is an animal. It's an animal. It does not do photosynthesis. It's an animal because it has to consume other things for organic material, right? You can see it here. Doesn't look like much to us maybe, but that is like other organic material. It's not producing anything itself. Compare it maybe to if you had a chef in the house, you wouldn't say just because you got to eat that meal that you prepared and made that meal. So just because the zooxanthellae lives inside of the coral, it doesn't mean that the coral is the producer. The coral is an animal. The next slide doesn't have as many words. Okay, so conditions required to grow. And this is where I say they're so entitled and they really can't tolerate anything. So their conditions required to grow, there's going to be 6. One is the water temperature. It's like the most important factor, the most important. So that's why climate change is such a hot topic for corals. And the fact that water is able to absorb a ton of heat, which you should have covered in the open ocean notes. The fact that it helps maintain climates and it stores a lot of heat. It's a good like temperature buffer. So their temperature range is 16 Celsius to 35. I put it in Fahrenheit. Don't ever answer in Fahrenheit. We are really one of the only countries that use Fahrenheit, and it's not scientifically like appropriate. So 61 to 95. I just put that there just so you can have something to consider. Their preferred range is 23 to 25. I remember that because, shoot, hold on, this is embarrassing. It was because of professional basketball players' numbers. It was LeBron and, gosh, it's 25. Is it Kobe? No, it's not. Okay, I'm not going to look it up anymore. But I always remember 23, LeBron, and then it's 25. Derrick Rose, that wouldn't have mattered. Anyways, dang it. Okay, forget I said that because I don't go back and edit these, so. Dang. All right. Anyways, the depth. They need to be within 20 meters of the surface. That's not very deep, but at 20 meters, they're going to be able to absorb all light wavelengths. In A level, we talk about like light penetration with depth, a little bit more specifically, but at 20 meters, you're going to have all different wavelengths going through. So red, orange, yellow, green, blue, and your violets. Green doesn't matter because chlorophyll doesn't absorb green, but your zooxanthellae, and I said again, your zooxanthellae has more than just chlorophyll, which is why it can have so many different colors. They need strong light intensity. Strong. So if there is sea level rise due to climate change, they're going to be deeper than they prefer, which would cause them to be stressed out. They wouldn't like that, but
See where the Nintendo Switch is?
I don't. It's probably charging.
It's not.
Okay. If there is some kind of sea level change, or as we'll see in a couple of more slides, like how there's different kinds of reefs, they start to grow upwards. They build on themselves. Your hermitopic corals, the reef building corals. So water temperature, it's got to stay warm. 23 to 25 is their preferred. I find those numbers just easier to remember than that range of 16 to 35. I don't know. That's me. Water depth, it's got to be shallow within 20. Water clarity. Water has to be clear. So I mentioned too a few slides ago that this is why having the zooxanthellae inside of the coral to be able to do photosynthesis and produce glucose is such a benefit, because there's really not enough organic material, detritus, just marine snow floating down. There really isn't a lot of that at all in the coral reef, enough to sustain that kind of population of corals. There isn't enough to be able to filter feed out. And if there was that kind of debris, there wouldn't have been this evolutionary relationship where zooxanthellae is inside of the corals, and two, zooxanthellae wouldn't be there because they would not be able to photosynthesize in an area that is turbid and cloudy. So clear water without silt or sediment or excess nutrients. Areas of upwelling, not going to work for two reasons. One, it's going to bring up a lot of nutrients that have sunk to the seabed, and it's going to make the water really cloudy. Two, remember, upwelling is movement of cold, nutrient-rich water from the seabed to the surface. And the cold water coming from the seabed is so cold, they're not hanging out for that. They would leave. They can't be in areas too close to the coast where there is coastal runoff. So where you have freshwater river flow, or even an estuary that's bringing in any sort of dissolved sediments from land. Okay. Sediment will scatter light. So this is the whole reason why sediment scatters light, which is why things look cloudy. It's because light literally gets ricocheted off of them. This increases turbidity. In addition, this can also, when it starts to land, it can land in the coral polyp's mouth and block light that way. But also, if it was to filter feed or try to use its tentacles to grab actual food source like zooplankton or phytoplankton, it couldn't because its mouth is clogged. Excess nutrients from runoff can cause an algal bloom, because that's really what causes it. When you have excess nutrients like nitrogen, phosphorus, potassium running into the water, algae take that up, they absorb it and they reproduce like crazy. An algal bloom will cover the surface of the water, preventing light penetration. Algae can also grow on the coral itself. There should be other herbivorous fish there, though, that's able to literally eat the algae off of the coral. With all this being said, this is really nice why we have mangroves to be the intermediate between river estuary flow and then your corals that are off of the coast, because they're going to slow down that water flow. Sediment, including that dissolved nutrients, are going to settle out, and the water going to the coral is going to be more clear. Corals are not a littoral zone. They cannot tolerate tidal changes. They cannot. They can't. They don't. They're not a littoral zone. They are coastal. They're off the coast. The remaining three, not much to write about. In the picture here, you have a lot of hermitopic corals. This is staghorn, like a deer. The substrate, it needs to be hard, dense, something for them to be able to cement themselves to and attach, because they're adult form, they cement themselves as substrate. Being near dormant volcanoes is super ideal, and that's where we see a lot of them, provided they're in tropical areas. The salinity has to be 35 parts per thousand, which is your average ocean salinity. We know estuaries can increase increase salinity higher than that. So again, these are not in an estuary. These are not in littoral tidal zones. There can't be any brackish water, which is estuarine, a mix of fresh and salt, and it can't be near fresh water. The pH needs to be slightly alkaline, so not acidic. It needs to be above 7, which is neutral, which means it's alkaline or basic, but we'll call it alkaline. 8.1 to 8.5 is their preferred salinity range. If the pH starts to drop, this will stress the corals because, like we talked about in first semester, CO2 in the atmosphere will dissolve into the water. And when CO2 mixes with water, it creates carbonic acid, and it starts to make the ocean more acidic and move it down from being in this alkaline range to a more acidic range, or towards your acids. That's a problem because the carbonic acid will start to dissolve the calcium carbonate shell, and it'll literally start to erode it. It's like if you have heartburn and you take Tums. The heartburn would be like the ocean acidification. The Tums is the coral shell. Okay. When talking about reef formation, there's different stages that reefs will go through. Tropical coral reefs. There are different ones. There is a cold water reefs. Obviously, they're not as talked about or popular because they're deeper. They're much deeper because they're cold water. So it's on the seabed. They're not. I said they're not as biodiverse just because of the conditions. That's it. There's no zooxanthellae there because they're so far down that there's no sunlight. So it'd be hard for humans to go and dive and like really appreciate. And yeah, no zooxanthellae because of the sunlight. So those corals are purely doing like the coral job and filter feeding. So why I said this, 5 steps to like a tropical coral reef formation. Okay, so Charles Darwin, the same one that, here we go, the same one that made all these different observations about plate tectonics. He made these observations about corals, around islands. And he started to see like this kind of formation. I'll move myself over there. Okay. So we started to see like this kind of formation, starting with like a dormant volcano. And I realized that this isn't yet dormant, but it will be. A volcano produces like very, very dense igneous rock as soon as it solidifies. So that right away is going to be a good substrate. And we're emphasizing tropical coral reefs because it needs to be warm. Okay, so volcanoes go dormant. They're very heavy because it's not like you have this like low density hot magma that's moving up. Once it's dormant, that magma that's left in there will solidify. Well, hot things are less dense. Colder, solid things are not as dense, are not as low density. They're heavy. They're very heavy. So this heaviness is going to cause the volcano to start to sink because the volcano's dormant. Nothing is really heating up that magma anymore. And so it solidifies. It's adding to the mass. Volcano's heavy. It will start to sink like within the seabed. This is called subsidence, or the volcano is subsiding, but subsidence, sub meaning below, but it's subsiding. The corals, as it starts to sink, and it's not like it just falls, that's not realistic, it's going to slowly sink. As it slowly sinks, the corals that did grow on the sides of it are like, oh no, we're getting out of the sunlight. They will start to grow on top of themselves and get themselves like closer to the sunlight. When they do this, because the volcano is not sunk that far, they create a fringing reef. And like to be literally on the fringe of something is like right on the edge. Like a fringing skirt, like a grass skirt is fringy. It's right on the edge of like your waist. A fringing reef. The coral is really close. You can tell because it looks like it might be sand. That's coral underwater. It will continue to sink. F. Okay, it will continue to sink. As it sinks, you're going to start to form a lagoon. Like water is just going to like fill in that gap from like where the volcano is going down. It's going to start to fill in that gap. So if I emphasize, my gosh, wait, oh, I guess I'll go around it. Come on, I'm sorry. I'm literally chasing this thing around. Gosh, okay. Over here, so on the left side, you can see the volcano sinking, right? And then there is a lagoon that's starting to fill in that gap. The lighter color that you see that even has palm trees on it, it actually, in this picture, there's a gap. Like you can see there's an obvious gap between the coral and the volcano. And I think it was just done in that picture just so you can see like where the volcano's going. But it's connected to it. The corals aren't floating. They have to be connected to something. Their old version, like their old skeleton of previous corals, like they're connected to this. So they'll go very far down, very, very, very far down because they can continue to grow on top of themselves. So when you have this gap area, water, like from the ocean, is going to fill in that gap and it creates a lagoon. This is a barrier reef because the lagoon is creating a barrier between the old volcano, where you have land, and the reef. Barrier reef. There is a barrier between where the volcano was and the reef because it's just further sunk. So like in this picture, can I get a pen? Yes. Okay. This part that we see right here would be like this part right here. It's like your tallest area. The rest of it has sunk. Moving on, it's going to sink even further. As the island completely sinks, there's nothing in the center anymore. Like I imagine though, like isn't there going to be like a time where there's just like bloop, like just the tiniest top of that and you're like almost walking on the plant, like the vegetation? Ollie? Olive? You good?
I was gonna sit on my chair, but then it just somehow scooted. And I fell down.
You're okay?
Yeah. I hit my back.
You're going to make it?
I'm good.
Okay, thank you. Okay, so the island completely sinks. The coral, meanwhile, is as it realizes it's getting further from the sun, they grow on top of each other, grow towards the light. They want to be within 20 meters of the surface. What remains there is this central lagoon. Wait for it. It's called an atoll. There's no land in the center at all. People also call it an atoll. There's nothing in the center atoll. That's fine. But that's a quick, easy way to remember that. Nothing in there at all. The lagoon can get very deep. I have some different pictures after these that shows like that just very dark blue, and it looks like it's very deep. It's because it is very deep. It is very deep. It's like the grave of a dormant volcano. But then it's crazy to think this coral that has grown all the way around here is like the offspring of the offspring of the offspring of the offspring of the coral that was growing, starting to grow here and definitely growing right here in the fringing reef. And it just continued to like build and then build and build and build and build and build as this started to sink further. Okay. If you feel confused, check out some YouTube videos. I have them. Not all these details are tested details. If you look at your syllabus learning outcome, I know it also says like to do that, to know this in terms of its relative location to the lagoons. Oh yeah, I don't think I put that in the slide. It's fine. I've given to you guys in class. Okay. So a little more details with it. The fringing reef. All reefs begin as fringing reefs. They're right on the fringes. So they can form on the edges of continental land, on the edges of islands, or oceanic volcanoes. Great. The only like main things they need to have are these things: water temperature, water depth, clarity, having the right substrate pH and salinity. That's all cool. Then this is where they can grow. Fringing reefs are separated from the shore by a very tiny, narrow, small lagoon. Like it's little. It's very little. Some people can walk across it. It's little. I put an arrow there. It's little. But being near to shore, the corals being so close to shore, because if you have people living on this island, it's going to be vulnerable to sediment from runoff or turbidity. If people are living there, there could be pollutants mixed in there. Also, if humans are constantly taking a boat out, maybe dragging it over, that's going to be a problem. As it sinks, we have the barrier reef. Again, the barrier, there is a barrier between the reef structure itself and the landmass. And that barrier, the boundary, is the lagoon. This lagoon is just bigger because that volcano has sunk down deeper. Barrier reefs are separated by land with a deeper and wider lagoon, and this literally creates the barrier. The reef is further from land than a fringing reef because what it's growing on has sunk deeper. So, like in this first picture, you can clearly see the distance between where the reef is growing and then the island. They're very close. Here, there is definitely this deeper, darker blue boundary. That's just the ocean water filling in this gap from where we have the sinking of the island. And they will continue to build up on themselves as the volcano sinks. This does get dangerous and unnoticeably shallow. Hey, Ollie. Olive Grace?
Yeah.
Wash your hands, please, okay? I'm sure she's going to do it. It could get very shallow, and it wouldn't be very noticeable because the water's so clear, and you could run your boat into it. Okay. Patch reefs aren't necessarily a stage, but they can happen. You can find them like in the lagoon. So even on a fringing reef where the lagoon is very thin because the volcano isn't sunk that far, you can have a patch reef, just like a patch of coral reef. It's like a reef within a reef. You can definitely have them in a barrier. where you have a deeper and wider lagoon. And they also will grow vertically. They're growing up because they want to be closer to light. The atoll. So, island completely sunk. The coral reef resembles a ring shape around a central, incredibly deep lagoon. There's no more land there. It's just now the reef. There's no like land from the volcano. The volcano, it did grow around. Okay, yeah. Okay, I'm like, what? It did grow around, has fully subsided or sunk. The corals still build on themselves and grow up towards the light. So to see it all at once, okay, underwater volcano goes to the surface. Great. It's going to become dormant. A reef will start to form around the island. And it's when it's dormant. Because if we're talking about the salinity can be changing, the temperature can be changing, it can't be full of sediment, like then it can't be around an active volcano because as that magma goes in the water, it's going to change its temperature, absolutely change its salinity, make it very turbid. What comes out of a volcano, similar to, it's not the same thing, but it's magma, and magma is what heats up a hydrothermal vent. And then that really hot water is dissolving the crust of the earth. And what comes out of the hydrothermal vent is very acidic as well. Very acidic. This is also acidic. It's going to really change the local pH there. It's not enough to change the pH of the oceans, but like localized for sure. But as it's dormant, and we have the arrows now pointing down because that solidified magma was very heavy, it's going to start to sink it. And you can see the reef starting to grow where it's shallow. Sinks more. We have the lagoon starting to fill in. Sinks completely. This picture skips the barrier reef. I wouldn't vouch for it. I wouldn't write home about it, but just a quick visual. It sinks all the way, and now you have all the water filling in where the volcano used to be. You have an atoll. But this picture does skip the barrier. Another way to see it. See the volcano. Now it's dormant. It's going to start to form. I wouldn't have labeled that coral reef because that can't happen. As it sinks and sinks and sinks, again, you can see the white. So these pictures go together, but you can see this white or like lighter yellow area is the coral growing up. And then once it completely sinks, we have this deeper lagoon, and it'll just continue to get deeper. The pink is the coral growing vertically. There we go. Lots of coral here. So much of it. You can see all the patches of them. They're just deeper. This is coral. This is coral. Lots of coral reefs here. Even though it looks like it might be above the water just from the color difference, it's not. Patch reefs on the outsides. And then this atoll is the area that the volcano used to be. You have a lot of these in the Pacific and some in the Indian Ocean, especially like Oceania where the two meet. Oh, we're towards the end, so state the importance. Lots of things here, but you don't have to write it all word for word. Please don't. So they offer coastal protection. You already talked about that with mangroves, but they are coming from the ocean. These are the first line of defense. They will absorb about 97% of your wave energy. You don't need to know that number, but they absorb wave energy. They like take on the brunt of that wave, kind of wear it out a little bit, absorb the energy. It will cause wave height to be reduced. It's very important to prevent coastal erosion and to help prevent storm damage. Mangroves and seagrass beds will also benefit this due to having less, like a less amount of erosion, decreased amount of erosion. Because if the corals are the ones to first absorb all those waves. Then those waves are not going to be as strong when they come in towards a seagrass bed or they go into an estuary where you have mangroves. And the mangroves, of course, benefit them back by slowing water currents down in their habitat so that sediment is able to settle. That sediment does not get taken back out towards the coast where there could be seagrass beds or corals, and that sediment will make the water turbid and or deposit on top of those organisms, the seagrass and the coral. Importance for food and for income. So fish, mollusks, shelled organisms, crustaceans, the spiders of the sea, the roaches of the sea, they live there and they are a food source globally for people. And when you have like income wise, the fishing industry brings in about $6.8 billion globally a year. And again, we're not going to want to use the dollar sign on our exam because the dollar is American and this is not an American exam. Medicine, I mentioned in class, we can always say, like we did for the mangroves, that there are medicinal properties. There will be medicinal services or medicinal products we can gain from any shoreline, any of them, or any, not even shoreline, but any marine ecosystem. Corals and anemones are sessile. Again, that means they don't move. They're stuck. Sessile is stuck. So in order for them to avoid predation, they release these chemicals that like will tell the predator nearby, like, okay, better not because they have these stinging cells and like didn't go well last time, and it's they know not to mess around. Those chemicals we can extract, and it does help treat different ailments, arthritis, cancer, Alzheimer's. I know these seem like, when would I need that detail? Great question. There could be questions about marine biodiversity and why it's important. And of all the medicines that you're going to be introduced to soon, like the potential medicines, I would just like lock in on one. Know that you can use that as a blanketed statement for any of the ecosystems, but maybe have one specific one. And very soon you'll be introduced to some more specific ones. You don't have to know them all. Like just choose one that you're like, okay, I can remember this. Just in case. An extra mark's an extra mark. Recreation and tourism. Obviously, same with Florida though, but people travel around the world to see biodiversity and beautiful ecosystems. So when people go visit reefs, the tropical coral reef in of itself generates around $35 billion a year. So this is very limited, but it allows for jobs in hospitalities like hotel industry, food service, boating, diving, all of your outdoor recreational things. It's very profitable. How do we ruin it? So the causes of reef erosion. Describe how this causes corals to erode and the impacts that it will cause. Hindsight now, I may have wanted to make another column just for impacts, but these impacts are not specific to any of the types of erosion. When we are losing reefs, which is reef erosion, these impacts will happen regardless of the reason of why it's being lost. It doesn't matter. So the impacts, I would jot them down. It doesn't necessarily have to go in any one of these columns or any of these rows at all. If you lose a reef, regardless of the reason, the impacts are going to be the same. Reef erosion. So the types are going to be bioerosion, so from living things, acidification, temperature increase, physical damage, and sediment presence, or just like sediment being there. Okay, I'll move myself over here for now. So reef erosion, and I repeat this definition on every single slide, but if you're eroding, like you're moving to a new location, or in this situation, you are not gaining. In fact, you're losing. Even though corals are going to try and grow, they're losing faster than they can gain. Like you're cutting your hair shorter than your hair can regain its growth. So that is what erosion is for the reef. It's like the loss of its mass. Bioerosion is when this is done by a living organism. Okay. An example, the parrotfish. And you have one right here. It's not the most beautiful of the parrotfish, but oh, look at those teeth. It's got a good beak. The parrotfish and the butterfly fish eat the polyps of corals. The parrotfish have very strong teeth, and they will use their beak to bite off the entire polyp, the whole thing, because they want to eat the soft-bodied organism that's on the inside that has the zooxanthellae in it. In order to do that, they need to break into its home. And instead of breaking in, they just eat the home. The calyx, the cup that it sits in, and then you have your organism in it. They eat the whole thing. And then any calcium carbonate that they do ingest, they will excrete out in the form of sand. But if they're eating more coral than the coral is able to regrow, it's going to cause erosion. I have a picture of it here. You can see like where it has its favorite area to nibble in this bottom left picture. Another big example, she's a big one, the crown of thorns starfish. I want to say sea star so bad, but it's literally called the crown of thorns starfish, but it is a sea star. It's not a fish. Anyway, this is the biggest threat in cause of reef mortality in the Great Barrier Reef. Is because of the crown of thorns starfish. And if I say cot or cots, it's the crown of thorns, C-O-T, crown of thorns starfish. Reasons why this is such a problem. When you have nutrient-rich runoff from fertilizers or anything used on land or animal waste that's going into the water, it's going to cause a plankton bloom, like phytoplankton. The phytoplankton are the food source for the crown of thorns babies. So when there is a lot of crown of thorns babies floating in the water, you wouldn't see it. It would be in the form of zooplankton. They float. You wouldn't see it, but they eat phytoplankton. Animal plankton, zooplankton eat phytoplankton, plant plankton. And if the nutrients are what's going to cause there to be way more phytoplankton, which is food for the crown of thorns starfish babies, then there's more food for the babies, which means those babies are going to grow, turn into adults, and destroy the reef more. There's another reason. There are things that can eat the crown of thorns starfish. Some sharks attempt to do it and can be successful. There's also the giant Triton snail. I don't have a picture of it. If you want to look it up really quick, please do. If you're thinking what can literally eat the crown of thorns starfish, it's a soft-bodied giant Triton snail. It's very big, but it is soft. And so you're probably thinking, how does it not get punctured? I don't know. I think that all the time. But without predatory fish, like something that's going to eat the crown of thorns and keep its numbers in check, then it's just going to continue to destroy the reef. And can I zoom in? I can't zoom in. But in this picture on the right, I don't know what you're using. If you're using a computer, using your phone, if you like pinch a screen, you can zoom in. You could possibly tell. I'll draw like the barrier line, but there is an area where you can see that there is like a difference in the thickness. So here it is much more thick because you do have like your organism still living in there. And like everything here, all in this area has been eaten. And you can see its little tube feet that helps guide it. It also allows it to stay attached to substrates or allow it to float a little bit. But in the middle of them is their stomach. Their stomach is just going to like almost, for us, it'd be like vomiting, but it's going to release digestive, like gastric stomach enzymes on whatever their food source is right from under them. And then once it starts to digest, like suck it back in. It's not uncommon. There are a lot of organisms that will like release like a fluid that's going to start to like liquefy their food source, and then they take it back in. Flies? I think flies do it. Okay. That one had two examples. That was the bioerosion. Ocean acidification. Again, bioerosion. We're losing more calcium carbonate than we're gaining. So a decrease in pH. This is caused by combustion of fossil fuels. The decrease in the pH or the increasing acidity over time will cause dissolving of calcium carbonate from the atmosphere. We've written this a lot of times now from this class. CO2 dissolving in the ocean creates carbonic acid, and this acid will dissolve the calcium carbonate skeleton. Could result in bleaching. There's a lot of coral death. Other things. So we know that temperature is the most important thing, being in that range of 25 to 23 to 25 degrees Celsius. That's their preferred range. Increase in temperature and climate change. So when conditions are not perfect for the zooxanthellae, they get stressed, they will expel themselves, like literally just move. Common stressors for them from the ocean is going to be an increase in ocean temperatures due to global warming and a decrease in pH. Both of those are caused by the same thing. Release of greenhouse gases or combustion of fossil fuels that release greenhouse gases, namely CO2. CO2 will dissolve in the ocean and cause carbonic acid, which will dissolve shells because of ocean acidification. CO2 is also locked in the atmosphere, and it will cause there to be an increase in global temperature because carbon dioxide is like a blanket for the planet, and it's maintaining heat and it's keeping in heat instead of allowing to escape. It's like blanketing it. Or like a greenhouse. They could have called it a blanket effect, but greenhouse. Greenhouse traps heat. Zooxanthellae gives coral polyp their color because of many photosynthetic pigments. When zooxanthellae leave, just the skeleton is going to remain, and the coral polyp, like the coral animal itself. But it no longer has like the live-in chef, and it's going to have to get food on its own, except there's no food to actually get in that area. There's just not enough to sustain everything. There's not enough things to filter through the water if they were going to do like their first job, their first role. Instead, they'll start to die because there's just not enough to sustain all those corals anymore. If their chef or their zooxanthellae leave, please don't call it a chef. And that it'll cause there to be erosion because they cannot build on their skeleton anymore. So over here, it's time-lapsed, but you can see a coral squeezing out zooxanthellae. It's like a sneeze. And you can see the chlorophyll within it. And it's bleaching itself. Sad day. Easy one. Physical damage. If there is a low tide, mainly during a spring tide, or if you have like, I don't know if you remember this, but like a king tide. A king tide is when you have a spring tide. So your high tides are already high, your low tides are already low, but then you have a tropical storm, or you have a tropical cyclone, which is a hurricane or it's a typhoon, but they have low air pressure. That low air pressure can cause flooding in some places, but it'll literally, the wind from the storm is pushing water towards the shore, but that means it's that water is leaving somewhere else. So this is very situational. It doesn't typically happen. You can tell it doesn't typically happen because we still have corals, despite also having tides. But too low of a tide could cause desiccation. Situational. Storms and hurricanes could cause the reef to physically break, and when sediment gets stirred up and it's not deposited, it literally is like sandpaper, and it's physically abrasive. It could cause the reef to also erode. Humans can step on them, take them home, not me. They can anchor boats to coral and not actually go to like a marina or an anchorage, a place where they can anchor, and they end up anchoring it to coral. Okay, recovery from hurricanes can happen, and I'm reading back in the middle. It does depend on the amount of coral that's remaining. Makes sense. The amount of sediment that was stirred up. If there's growth of algae now, And if that algae is competing for attachment on the reef, like attaching onto like a hard substrate, if it's covered by algae, then that spot's taken. Will also recovering from a hurricane will also depend on what kind of toxins were involved in the runoff. I can do it. If there was a lot of fresh water discharged into the water, now the salinity is too low. There's an algal bloom again. If there's a lot of sediment runoff, this happens to us all the time because we release our wastewater into the Indian River Lagoon, causes an algal bloom. It's either that or letting all that water during a storm, like a hurricane, letting all that excess water flood houses. That's not good. The presence of sediment is also going to cause erosion. It's going to prevent feeding. It's going to prevent light energy as well. Okay, so you have a comparative picture. So again, sediments can cause high turbidity. High turbidity is going to cause low light energy, light penetration. This will cause productivity from photosynthesis by the zooxanthellae to be so much lower. So we're not synthesizing glucose at the same rate. Sediment can also settle in the coral polyp's mouth. That would prevent the coral from feeding directly because it's blocking it. And without me typing it, if we have lower productivity from less light energy, that means less glucose, which means less food source for corals to actually use to grow themselves. Here's the impacts. So again, it doesn't matter which one we link this with. No matter any way that the coral is eroded or we're losing coral, these impacts will be the same. So mainly there's a big economic risk. Habitats will suffer. We're going to have biodiversity loss, and biodiversity is important to maintain all ecosystem stability. You do want a lot of organisms there. Habitats will stop. I just said that. Human communities will experience more erosion from waves and greater storm damage if we don't have corals there to be a line of defense with the waves. Marinas will get damaged. Cambridge refers to these as anchorages, a place where you can anchor, but they are marinas. The cost to rebuild goes into the multi-millions, and that's a problem for humans. And if we want to then implement artificial structures, that gets very expensive, and somebody has to pay for that, and it's going to be the government. Or it's not going to be the government. It doesn't happen. And this is to use artificial structures like a break wall or a seawall. Instead of using something that's already a natural defense. Putting in something man-made is very costly. The loss of money from less tourism is also a problem. A lot of areas in Florida experienced this after Hurricane Nicole and Hurricane Ian, and not all those places are already redeveloped yet either. We're going to have less food. If that's something that we can make money from the previous slides, why they were important, then it's something we're going to lose money from if we don't have them. And if we also are able to get medicine from them, when we lose them, we're not going to be able to get medicine from them. So what do we do? How do we try and fix it? I think this is the last slide. I'm so tired. Artificial reefs. This is how now off areas of Florida, they can have some corals growing because Florida does not have a rocky substrate. Florida is very sandy and soft, and you can't have coral attached to that. Okay, I paused it, Tion. So people, companies, government can implement artificial reefs. This will increase biodiversity and give more ecological stability. If fish populations start to increase because now they have more of a habitat, they have more of a niche, and they have more of a food source there because you have producers again now. Again, your producers, namely being the zooplankton. If producers are there, the rest will follow. If there's more fish, then the fisheries or fishing companies will have more money. And this will also give the locals a food source as well. This will help reduce wave energy and height. That was the whole point. This will prevent marinas from having damages, boats that are at marinas from being damaged. This will stop a lot of shoreline erosion, and this ultimately will save taxpayer dollars. And it will also, although this may not seem evident to you right now, this will also help limit the massive increase in homeowners insurance once these happen. That's always something that is a big thing in Florida, is the cost to insure your house. And every time there's a big storm that goes through, you can be sure that insurance is going to go up. Artificial reefs get placed in areas that wouldn't have a rocky substrate for attachment, provided that it's warm, right? All the other things that they need to be like good conditions for growth. It's warm, it's not by a river, it's not directly by a coastline with humans. So these can be made of non-toxic concrete. This can be made of sacks filled with sand to try and keep them in one place and not have them float to an area that is now going to be out of their conditions. This could be stone blocks or sunken ships. So I'll just touch on the sunken ships really quick. Down here, it's actually a tank, but deliberately sinking those that are out of commission, you'll remove if there's any like toxic paint that's on there. Sometimes companies will do this to prevent mussels and barnacles from attaching and slowing them down. That can be toxic, but they'll scrape that off. They remove any electrical infrastructure in there, electrical structure, take out any batteries, any oil or fuel, and really just like strip it down. But if it's out of commission, you're not going to reuse it, then they sink it deliberately in a specific place that will be sustainable for corals. And then they can attach them on their own to help recolonize it. Looking up here on the right, the Cancun Underwater Museum in Cancun, Mexico. So old statues sunken. And that is a great service because it's not just like dense and hard, it's rough. So there's areas that it can definitely attach to. Smoother areas are hard to attach to. The GIF in the bottom left corner, you can see that the construction of it, that's not cheap. I think when I read the caption for it, they were like building it's 3D printed with whatever material that they're using. And they're building it themselves, but that's not cheap. The materials to even take them out there to be able to do this, like someone's paying for that. The fuel for the boat, all the gear that they're using. It's not cheap. In the middle, this is like your typical reef ball that is used a lot for reconstruction and building an artificial reef. That takes a lot of skill. It takes people that you need to train, or if they're already trained, then you need to hire them. To get those reef balls from the place that they're made on land, because they have to be made on land, to a truck or directly to a boat, that takes manpower, that takes machinery, that is expensive. Then they're very heavy. You got to put them on a boat that is going to be able to withstand all of that mass and all of that density of those. That's expensive. The fuel to get out there is expensive. The equipment needed to lower it, because you don't want to just spend, like, these things could be like $6,000 to $30,000 depending on how big they are. Not $6, like $6,000 to $30,000. To be able to lower it into the water is also quite a task. That also requires a lot of machinery to get it in the right place. And then they typically will like drill it into the ground or anchor it or attach it with like really thick chains. And then they can start to actually like attach and secure coral polyps that they've probably been growing in a controlled area. They can attach it there so they can start to colonize. But none of this is cheap. Let's not ruin it. I'm really excited to get to go to sleep now. Thanks for joining. I don't think there's any more slides. There's not. Okay, good.